Let me share the screen. So let us discuss on the implementation of linear time invariant systems, their structures and realization. Okay, I will very give an overview based on the previous video lecture I have sent. Okay, then I will give you some time to ask any specific questions that you have on this topic. So far in the previous discussion, we had seen how to analyze the signals systems, both in time domain and in frequency domain, especially focusing on the discrete time systems and signals. Okay, so in this topic, we were discussing on how to realize the system, how to open up this black box. Okay, what should be inside of this and how should it be realized. Okay, that's what we wish to see here. Okay, so in general, any linear time invariant system, we have a input x of n and impulse response h of n. The output is obtained like this, and in frequency domain like this. However, if we would like to represent in input-output relationships, we can have a general expression that is y of n relating onto the x of n and its delayed versions, and y of n delayed versions. Okay, and this general expression not necessarily limit to LTI systems, and it can be for any systems. Okay, and then this is a specific example with only few terms. Okay, in Z domain, the transfer function, general transfer function looks like this, where this polynomial, numerator polynomial defines what are the delay coefficients and the delays associated with x of n, and the denominator polynomial denotes what are the coefficients, okay, and the respective delays associated with y of n. Okay, so this can also be represented in terms of the pole zero form. Okay, where the poles can be explicitly seen here and zeros can be explicitly seen here. This is just factored like this, okay, to have a representation. Sometimes this is preferred and sometimes this representation is preferred. Okay, so then we have seen actually there are two categorization of systems based on the nature of impulse response or the transfer function we have. So if you have only numerator polynomial, we call it as FIR systems. If you have both of them, we call it as IR systems. The reason being, if you have only numerator polynomial, it turns out to the finite impulse response. That is, there are only finite terms in the impulse response of such systems. Okay, and then if there are infinite terms, there is a denominator term. This gives rise to infinite terms, and hence it is referred to as infinite impulse response. And this is a specific example, finite impulse response system. Okay, and you can see input-output relationship and so on. Okay, so we have seen how to realize such system. Okay, especially in computer, when we want to model any finite impulse response system, these coefficients will characterize everything, because the number of non-zero coefficients will tell how many degree of delays we have. Okay, and the coefficient values also will be here. And this GI equal to 0 indicates there is no denominator, and hence it's an FIR system. Okay, and to realize this, what we said is there are few primitive elements that are required. Okay, that are referred to as the delays, multipliers, and adders. Okay, so before that, we also have discussed an example of IR system. For ease of understanding, this is the simplest IR system where you have infinite terms, even though with a single denominator term. Okay, because this, when you express in terms of the polynomial, it goes to infinity, right? And you can see a general system impulse responses like this and so on. Okay, so for realization of this, as we said, see, if we have impulse response like this, our input-output relationship like this, what we need to do is output should be function of x of n, b0 times x of n. Okay, b1 times x of n minus 1, so there should be a delay. b2 times x of n minus 2, there should be another delay, both multiplied with b0, b1, b2. These three terms should add up to get yn. Okay, as you can see here, the primitive elements that are required for realization of any FIR system or even IR system are delays, multipliers, and adders. So the whole hardware technology is based on this, how effectively you do delay. Okay, so with yeah, very less time, how do you make a delay happen? Okay, with very less like very fast computations and so on, with and accurately, how do you do multiplications? Because see, these are all floating point numbers when you do at the end. So even with small errors here, okay, multiplying with, say, you can't do it with infinite precision while multiplying. So 0.2 means 0.20 may come sometimes, 0.999, 0.1999 may come sometimes. Okay, something like that. Even these elements will be like this. So the multiplication answer also will be, again, it cannot be at infinite precision. So all these things matter when you realize. Okay, so but these are the primitive elements with which we realize any of the FIR system. And we also have seen a general FIR system having m delays and m+1 m multipliers and adders. Okay, so usually one problem that is of interest in this area is to calculate the cost required for implementation. That means, say if I give you some function, okay, some transfer function like this, or the input output relationship like this, okay, how many adders, how many multipliers, how many delays are required? And if the cost of delay, cost of multiplier, cost of adder is given to you, what is the effective, like what is the cost that is required to realize it? Okay, and which implementation will give how much cost, and so on. Okay, as I said, there are two different ways of implementation, direct form 1 and 2. Okay, when we consider IR systems, it will be more clear. So this is an IR system, a small example of IR system, wherein you have actually, we want to realize this input output relationship. Okay, so y of n has to come like just like FIR system, considering these components, that is the numerator components, with delay for the inputs and the multipliers, and then delay for the output and corresponding multipliers. Okay, and this you can see that it is numerator and this is the realization of the denominator. Put together, you get the total like IR system, right? Here also you need only this, and this can be realized in different ways. You can see that here there are two delays. Again, here there are two delays used for delay of input and output. If we switch this to this side somehow, can we combine them? Okay, it can be combined by interchanging the like realization of numerator followed by denominator to denominator followed by numerator. Okay, and we can make a small change of variables here. First you realize, okay, denominator, and then you realize the numerator. Okay, and this is referred to as direct form 2. Okay, which you can see here, where denominator is realized and then the numerator. And you can see that the intermediate variable here shares exactly same delays, okay, and the same delay component. Okay, so you can club them. Okay, and hence you can save half of the delays. Okay, so as we have seen, this is referred to as direct form 2 implementation. And this is known to be one of the effective implementation. So there are some transpose forms. Okay, by transposing x and yn, you can change the whole like directions and so on. Okay, but they're also quietly well known, but I think we don't bother right now on that. Okay, so in this, as I said, the one of the key problems or important problems in this area are given a transfer function or input output relationship. Okay, and the cost of each of them, you should need to know how many multipliers, delays, and adders are to be taken, and finally calculate the total cost required for implementation of a system. Okay, and one more thing that is usually of interest for the discussion is, see, if you have a big system, okay, if you realize so on, so on, so on, and so on. Okay, even if there is a mistake of, say, even if there is a overflow through multiplication at some point, okay, it will affect all the multipliers. Okay, so whereas, see, for example, if one BK is affected here, then what will happen when I bring into like zeros and zeros here, all the zeros will have this effect. See, if I have an equation having, say, if I have a numerator polynomial with, say, 10 degrees, among the 10 degrees, coefficient of fifth coefficient is affected. It means that all the zeros of it will get affected. Whereas if I break already into like roots, okay, and then implement even if this get affected, only that subsystem of h1 of z only gets affected, not the other subsystems. Okay, so same is the case even with the poles. It is more important because the stability of a system depends upon poles. say switching from 0.9 to say 0.99 to 0.10 makes a great difference in poles. Okay, so if there is a small implementation issue when we implement the signal that is to be obtained or multiplied, okay, gets a overflow or a underflow, it makes, that means slightly up or down, okay, its value, it affects all the quotients, okay, when we, all the poles when we factorize. Whereas, okay, here when we first initially itself you factorize and implement, in this case, okay, you can, even if there is a overflow here, it only affects this one, okay, like that. Okay, so cascaded, this is referred to as cascaded form, where you bring in second order structures, okay, and then implement. The advantage of bringing to second order structures is most of the times the coefficients will be complex. Okay, when there are complex coefficients, when you bring in second order system, okay, you will get real roots, real coefficients. Okay, for the second order, say 0.8 into e power minus j pi by 4. Okay, one side, 0.8 into e power plus j pi by 4 on another side. When you multiply both of them, you will nicely get something like, okay, 0.8 square. Okay, so complex things will become real when you bring two two roots together to a two corresponding complex conjugate roots together. That is the benefit. People go for cascaded structures. Okay, and you can see that cascaded structure means bringing each of these into second order structures and then implementing them. Okay, by direct form 2 or direct form like transpose direct form 2 and so on. Okay. So the other reasonably well-known implementation form is parallel form, wherein you can implement, you can again bring into second order structures, but here we decompose h of z as a sum of different second order structures. Here it is product of different second order structures. Okay, and hence each of them you implement like this and sum them. Okay, this has some advantages, but not as advantageous as cascaded structure. Okay, because this is not easy. You can't relate directly here to zeros and poles. Here only poles you can see very clearly. Okay, after even after poles of this are seen here and here as well, but zeros of it are completely different. Okay, when you sum the zeros, not necessarily be equal to the exact zeros of this polynomial. Okay, so I will stop here, and you are welcome to ask any questions now. Hello. Yeah, tell who is this Kartikeya?
No, so Harshvardhan, sir.
Yeah, ask
Sir, parallel form means we are taking by partial fraction we will implement, sir, that form.
Correct. We are taking partial fractions only. But while taking, after taking partial fractions, we group the complex conjugate poles. That's all. To have the second order structure. Realizing, as I said, it has, you see, if you want to bring a complex multiplier here, okay, at any stage, while realizing, if you want to do complex multiplication, how many operations are needed? Complex multiplier, how many operations? Harshvardhan?
Yes, sir.
How many operations you want to do complex multiplication for any, say, input signal coming in? One signal value coming in. If I want to do complex multiplication, how many operations are required? How many multiplications?
4.
Yeah, you are there.
Sir. Yes, sir. Yes, sir.
Yeah, input complex means then 4 are needed. Correct. So, but if input signal is real, then you need only 2 multiplications. But at least you need 2 real multiplications, right? For each complex multiplication. Okay. Whereas real multiplication means only 1, right? So that's why there is an multiply off. If you can bring out the quotients to be real rather than bring them. Is that clear?
Oh, yes, sir. Yes, sir.
Yeah.
Okay.
Right. So request any other questions or any other student to ask. Yeah. Kartikeya, is it clear? Is Madan there?
No, sir. Madan is facing internet issues. Electricity is not.
Okay. So if, Pradeep, Girish, any of you can quickly ask. Otherwise, I will wind up the discussion. Is it clear then?
Yes, sir.
Okay. Okay then. So now what do you suggest? Shall we discuss some of the questions on sampling, or you have any doubts? First, if you bring in 1 or 2 doubts at least, I would be happy. Yeah, any doubts? So Niharika, do you have some doubt?
No, sir. I didn't solve all problems. So.
Okay. Okay. Fine. Any other student? Bhargav?
No, sir, no doubt.
Okay. So I will give you one problem then. Okay. So let us take this problem. Yeah. So this is 4.5 problem in Oppenheim and Schaffer. So the discrete time system has a low pass filter. See, low pass filter in discrete time. Up to what extent will it be there? Say, what is the range in which I should show the I should sketch the response, frequency response. Quickly answer. Yeah, minus pi to pi. Very good. So it is from minus pi to pi. Okay. Minus pi to pi. Okay, assume that somewhere. No, I don't bother about exact my drawing. So, and it's what they have given cutoff frequency is pi by 8. What do we mean by cutoff frequency? What do we mean? It's a low pass filter. You agree, right? This h of e power j omega or low pass filter. Okay. And its cutoff frequency is pi by 8. What do I mean by cutoff frequency?
Up to that frequency, components are allowed.
Up to which frequency we pass the frequencies. Okay, we pass the input signal. Okay, so the frequencies in the input signal up to this pi by 8 are passed. This is omega c we denote with. Okay, right. So it's equal to pi by 8. That is given. Now the question is, okay, xc of t is band limited to 5 Hz. So there is an input signal. This is a system, right? So this is now a system. Some h of e power j omega. Okay, so for this, the input signal is x of n and x of e power j omega. So we don't have information on x of e power j omega. We have only information of x of j omega. Okay, continuous time Fourier transform of this signal. And what is the information we had is what? It is band limited with 5 Hz. That means what? So you can see that minus 5 to 5 kilohertz. Kilohertz. Okay, this signal is non-zero. In this region, it is some shape. We don't know the shape, but it is non-zero only in this range. Okay, spectrum. Okay, so and this is f, or say omega by 2 pi for our ease of understanding. Okay, so this is what is given. And what is the question is, what is the maximum value of t which would avoid aliasing for continuous to discrete time conversion? So what we want to do is, see, we don't want to give directly to a filter, right? So a discrete filter. So what we want to do now? So this, if this is x of j omega, okay, or xc of t, okay, what we want to do now? We want to give this to a what? Give this to what?
Discrete time filter.
Huh?
Discrete time.
Analog to discrete converter. Okay. So analog to discrete converter means what? What will be inside of this analog to discrete converter, digital converter or discrete converter?
Sampler.
Yeah, there will be a
Audio
sample, right? So the xc of t, okay, we'll have actually to, the other way of writing it is, you multiply with a sampling. Okay, delta train. Okay, delta train of t. Okay, capital T I will write. Okay. So let me write, yeah. Okay, there is a delta train I'm writing like this. To get us, so x c of xs of nt, okay, or we write it as x, by dropping this capital T, we write it as x of n. Okay, so this is what we get, correct? Now the question is, this capital T, okay, how much should it be to avoid aliasing this?
So 1 by 2f.
Yeah, one capital T should be equal to how much to avoid
1 by 2f.
1 by
2 into 5,000.
So what we have through sampling theorem is fs has to be, okay, greater than or equal to twice the maximum frequency in the signal, right? So here the maximum frequency is how much? So maximum frequency is how much?
5 kilohertz.
5
Yeah.
kilohertz.
5 kilohertz. Okay, 5 into 10 power
3.
10 power 3. Okay, and so this has to be equal to, so 10 into 10 power 3. Okay, and hence the sampling frequency is this much, and sampling time has to be, okay, has to be less than or equal to how much? 1 plus 10 into 10 power 4.
10
Right?
into 10 power 3.
Sorry.
So 10 power 3.
Yeah, 10 power 3. So sampling time has to be less. So maximum sampling time we can allow, maximum value of t that we can have is, okay, 1 by 10 into 10 power 3. Correct?
Sir.
Yeah. So now the next question is, if 10 equal to 10 kilohertz, this is actually t equal to 1 by 10 kilohertz, right? So 1 by r 1 by t is equal to 10 kilohertz. Okay, so just we have written as inverse. What will be the cutoff frequency of continuous time filter B? Okay, so if this signal has to pass through this, okay, what should be the cutoff frequency of the continuous time signal B? See what, like continuous time filter B. That means, see, if I want to map this small omega axis to capital omega axis. Okay, if you want to sketch this filter in continuous frequency, okay, what should be the cutoff frequencies? That's the question. What do you think I should do now? What should I do? You got the question?
Small omega equal to capital omega into T.
Yeah.
Relation.
But capital omega. Small omega is given here.
Continuous time frequency.
Yeah. Omega by capital T. Right? So you have capital T here with you. Okay, 1 by T is 10 kilohertz. Okay, so you should multiply with 10 kilohertz. Right? To get the spectrum here. Yes or no? How much should I get? Do I get? How much do you think I will get? Minus pi by 8 into?
It'll be 1250 pies.
Yeah. 10,
100
square. Okay, so this is equal to minus 1250, is it? Pi. Correct?
Yes, sir.
Yeah. Here also 1250 pi. Or 625 into 2 pi. Okay. So in terms of frequencies, the cutoff frequency FC is equal to 625. Correct? For the continuous time filter. Yes or no? Fine?
Yes, sir.
Yes,
Yeah.
sir.
Okay. So this is reasonably simple question. Okay, but this will be widely used when we design filter design. Okay, when we usually there is a specifications are given in continuous time filters. Okay, because continuous time filters are one which are operative. Okay, when you want to put some filter in action, you need continuous time frequency cutoffs and so on. Okay, you also need some other things there. Okay, but all in continuous time. But what you can do while designing mostly is discrete time, because we mostly design with computer. Okay, so transformation from continuous time to discrete time of the filter response, okay, of the is very much important. Also the implications on sampling are also important. Okay, fine. So let us take another question. Yeah, let me take one question. So this is given a discrete time signal. Okay, I will tell how we get this discrete time signal. Is sent to a upsampler, downsampler, and followed by upsampler and a filter. So now I suggest you people should tell what should I do. Okay, I will not tell the steps. Okay, I will just write the question and leave. Okay, I suggest you people to tell. Minus pi by 3 to pi by 3. Okay, height is 1. This is anyway h of e power j omega. This is a discrete filter. Okay, and then you get the reconstructed XR of n. Okay, after doing this process, here anyway downsample signal, and here is upsample expanded signal. Okay, and how you get this x of n is so they have directly given x of n in this case. X of n is equal to sine pi by 8 pi n by 8 by pi n, okay, whole square. Right. So the question is, x r of n is equal to, okay, x of n. That is the question. Now tell me, how do we do it? Yeah, Pradeep, will you tell now?
So we have to see that there is no aliasing when we do downsampling, sir.
Okay, fine, good. But how do I see it? Your answer is correct. So how do I see it? Okay, I request like
Our
Anjali.
omega will see, sir. Impulse. It is they are coming at plus minus pi by 4, sir.
Okay, fine, good. So how are you telling that?
So cos pi n by 4 we have input, sir.
What is that? Okay, I request other student. So probably Anjana, will you be able to tell what is my first step? I just want to solve this problem. Where should I start? If you can't tell, you can clearly tell that I am not clear, so that we will move on. Okay, you're not there or there? Okay. Bhargav, will you tell?
I think it's same as the input signal, sir.
You are telling answer. I am asking first step.
Sir, in case of downsampling, spectrum will be
No. What is first step? I am asking Bhargav.
sir, x of n is multiplication of that sync pulse, sir.
Okay.
In frequency domain, it's become convolution, sir.
Very good.
So
Anyway,
if
just stop there.
cutoff frequency becomes twice.
Yeah. So let us do up to there because I think we are with class. Okay. So you are saying what you have is multiplication of two sync pulses. Okay. And in frequency domain, if I bring in, it will be convolution of two what? Two convolution of what now?
Two rectangular pulses.
Two rectangles.
Two rectangular pulses of what width?
Minus pi by 8 to pi by 8.
Very good. Minus pi by 8. Okay. Here also a rectangular pulse of minus pi by 8 to pi by 8. Okay. I think by 1 by 8, I think height, right? So by 8 here. So it's okay. Let us leave it. So I think 1 by 8, I'm thinking is height. Okay. But otherwise, just the height is not very important for now. Okay. Right. Because anyway, final input and output, we just want to see whether they come same or not. Okay. So if we do this convolution operation, okay, we get some spectrum. Up to where do you expect that spectrum can be? I request now another student.
Minus pi by 4.
Pi by 4 to pi by 4. Okay. So minus pi by 4 to pi by 4. Okay. And what is the shape of the spectrum?
Triangular.
Very good. It will be triangular. Okay. So in fact, its height also will be 1. Though I have plotted if it is fraction, then it will increase. Okay. So it's okay. Some height. So we have this spectrum. This is spectrum. What is this x of now? E power j omega. Okay. X of e power j omega. Correct or not? My notation, is it correct or not?
Yes, sir.
Correct. Now come to the next step. Yeah. Who will tell next step? Tell your name and tell this step answer. If I now downsample it by 3 times, what will happen? See, I have a spectrum which is there from Okay, it is same. I am just sketching for my convenience. Minus pi by 4 to pi by 4. Okay, this is x of e power j omega. Now, if I downsample this by 3 times, okay, what will happen? Quickly, I need someone to help me.
Sure, it will expand, sir. Minus 3 pi by 4 to 3 pi by 4.
Right. It will expand from minus 3 pi by 4 to 3 by 4. Okay. And it will only expand. And is there any other thing that will happen?
Other terms will also come, sir. Other extra 2 terms will come.
Yeah, okay. So minus 3 pi by 4 to 3 pi by 4. So, yeah, other replica will come, as you said. But where does the other replica will come? So, do you want me to sketch somewhere here? Where does the other replica will come? This is my next question.
Sure, at 2 pi by 3.
Okay. Minus 3 pi by 4 to 3 by 4. Yeah, I need very good answer now. Where does the
Sure,
next
sir.
replica?
Minus 2 pi by 3 and 2 pi by 3, sir.
Okay. Pi and all the time next replica will come only at 2 pi. Okay. You go and observe now the previous discussions. Okay. In any case, the next replica will come only at 2 pi. Okay. So,
Yes, sir. Yes, sir.
so this is irrespective of the upsampling rate, because what will happen is, see, ideally what will happen, 2 pi by 3. So there is a shift of expands by 3 times, also shifts by, okay, shifts by 2 pi. So that 2 pi is after expansion. Okay. So it will be at minus 2 pi and 2 pi. Okay. And when minus pi to pi, if there is no aliasing, okay, that is good enough that we can assure that, that means if the first replica after expansion doesn't cross minus pi and pi, okay, then it means that there is no aliasing at all, even after downsampling. Fine. Does it cross minus pi to pi now?
Yes.
The first, does it cross in this case or not? The non-zero frequencies, do they go over minus pi to pi?
No,
No,
sir.
sir.
So that,
No, sir.
okay, no aliasing, because, okay, the after expansion, you can see that one, if you just notice one replica after, like one spectrum after expansion is good enough to judge whether there is a aliasing or not. With aliasing, how is a pattern? If you wish to draw, then you need to have the replicas around. Otherwise, this itself is good enough to tell that there is no aliasing. No aliasing. Okay. And it is perfect now. Okay. Because this anyway, you can put a filter. How much is the filter that you wish to put now? Still filter is not there. So after this, what's happening now? There is a upsampling by 3 times. Okay, what should we do now in upsampling? For upsampling, I want to do upsampling now. What should I do? Tell me quick.
Sir, it will shrink by 3, sir. Minus pi by 4 to pi by 4.
In time, it expands by 3, and hence in the frequency domain, those who are not talking, please mute your phones. Okay, now it is minus pi by 4. So it comes back again to minus pi by 4 and pi by 4. And where will be the next one? That is important now. Okay, because see, there is a filter here. Here, after this step, they have given filter from minus pi by 3 to pi by 3. In some cases, if they give from minus pi by 4 to pi by 4, or minus pi by say minus pi by 2 to pi by 2, okay, then we need to see whether this spillover things will come into the spectrum or outside the spectrum, or this spectrum is completely captured or not. So you should sketch the next replicas also before applying to spectrum. Okay. So what is this value now? Tell me. 2 pi minus 3 pi by 4. That comes to what? 2 pi minus 3 pi by 4. Huh? How much?
5 pi by 4.
Now, shrink by 3 times. What will happen to this? Where does it come? Now, shrink by 3 times, and hence it will come at 5 pi by 12.
12.
Right? 5 pi by 12. Okay, so 5 pi by 12. 5 pi by 12 is close to how much? Okay, this is pi by 4. Okay, so this is pi. Pi will come at pi by 3. Okay, previously which was there at pi, now comes at pi by 3. Okay, and equidistant from that will come 5 pi by 12. Okay, fine. Okay, so here you will have the next.
Yes.
Right? Same is the case even here. This is what? Minus pi by 3. Okay, and from here you will have the next spectrum. Okay, and this one minus 2 pi by 3 and 2 pi by 3. Okay, fine. You should sketch this before like applying the filter, so that you will be able to know which are the things which are like which will come out of the filter now. So now with this, what we do? We apply a filter. Okay, what is the filter frequencies? Minus pi by 3, 2 pi by 3. Okay, and hence what will be the output now? What will be the output? Huh?
Minus pi by 4 to pi by 4 replica will come. Only that one.
Click at minus pi by 4, pi by 4 will come out. Okay, minus pi by 4 to pi by 4. So is this the original signal? X of e power j omega back, right? So,
Yes,
so
sir.
this, yeah,
Yes,
this X
sir.
of, so you can see that this X of e power j omega, and hence X r of the e power j omega is equal to X of e power j omega. Okay, this is X r of n. Okay, and hence X of n. So what we are sending is X of n, and what we got output X r of n is equal to, that implies X r of n is equal to X of n. Okay, is this clear now?
Yes, sir.
Yeah. Okay, so this is step 1. Okay, step 2 and step 3. Okay, in this. So 1, 2, 3. Okay, fine. So, fine. So probably another last question. If you have any question, those who have worked out, you are most welcome to ask me. Otherwise, I will tell which questions which are convenient for me. Okay. So let us take this question now. So here, h of e power j omega see, this kind of multi-rate systems are very important. In many of the practical scenarios, okay, you need to do upsampling, filtering, downsampling, and several of these conversions in between. And you are asked to tell what will happen at the input and output. Will there be any, say, which are the frequencies lost, which are retained, both are same or not, all those things. Okay, so here, because of the basic problems, this is a simple question, but there are several of questions of this sort, which you can see later in this book itself. Okay, so let me take another question. So this is 4.12. Okay, in the Oppenheim and Schaffer, whatever I have discussed, this is 4.15. 15C. Okay. So B I am discussing now. A and B also I will discuss. H of e power j omega here is equal to j into omega by capital T. So if this is given to you, can you comment on the system? What kind of system is this? Yeah, think of. Okay. So you have xc of t, which is given as, okay, cos 6 pi t. Okay. Oh, this is the first question. For second question, it is cos 14 pi t. I will tell that later. Okay, and this xc of t, first anyway is analog to digital conversion done. That means there is a sampler and so on. Okay, sampling with capital T. Okay, and this capital T is equal to 1 by 10. Okay, and this is given as input to A. After sampling, what you get is x of t, you converted already, x of n you got. Okay, this x of n you are giving as input to h of e power j omega. This system. Okay, and getting some output. That is y of n. Okay. And after this y of n, we assume that we applied. So again, we use the information of t. Okay, and converted to digital to analog converter to get yc of t. Okay, this is the whole system. And the question is, find yc of t for this example. Okay, first question is find yc of t, and can you comment on the operation of this system? Yeah, I request you people to answer. B, this is all whatever we have discussed is A. B requires xc of t is equal to cos of 14 pi t. Okay. And same question. Say, repeat. Finding yc of t. Okay, and comment. Yeah. So I request one of the students to start the discussion. So how do we start first? What is our first step?
So convert xc of t to x of n.
Very good. Convert xc of t. Okay. So who has told this?
So Harshvardhan.
Yeah, very good. So there, see, while converting, what do we look at? So we have xc. I want to convert to x. Okay, tell me how to.
We will convert t to n by t. Nt.
Okay. So for converting xc of t to x of n, what we do is replace small t by capital N into t. Okay, that is equal to n into t is 1 by 10, right? N by 10. Okay, so x of n now I can write it as cos of 6 pi into n by 10. Okay, so this is equal to cos of 3 pi by 5 into n. Fine. The question here is there an aliasing that has happened while doing?
Sir, no, sir.
No, because the maximum
F
frequency
is
of
3.
signal xc of t, fm here is equal to
3.
3. Okay, whereas Fs is equal to
FS 10.
10,
10.
which is 2 times F. Okay, so no aliasing. Good. So this is a good inference here. See, at every step, making some inference like this will help. Okay, to give inputs for the later steps. Okay, good. So now what is the next step for me? I got x of n now. Okay, x of n now is equal to, okay, cos of 3 pi by 5 into n. I got this. Then what is the next step for me?
We find x of e power j omega.
Okay, I can find x of e power j omega. So I will find, say, x of e power j omega. What will be x of e power j omega in this case?
So we get impulse.
I can find anyway x of e power j omega, but do I need it? Can't I do without finding x of e power j omega explicitly?
Write x of n in terms of the exponential.
Okay, write x of n in the exponential, and then what should I do?
Use the eigenfunction property.
Right, use the eigenfunction. Okay, that's what usually is preferred, because, okay, this is h of e power j omega, right? This is a like exponential signal, okay, or a cosine signal, which will have the eigenfunction property. Okay, so what we do is e power, okay, j. In fact, cosine signal directly you can use. Do you people know how to write the output for a cosine signal if h of e power j omega is the frequency response of the system? Cos of what will happen for the output?
So angle phase will change, plus angle of h of e power j omega will be added, and we multiply with the magnitude of h of e power j omega.
Very good. So we'll do that. So we will directly write that. Those who are not familiar, split into complex exponentials. Okay, e power j 3 pi by 5 my plus e power minus j 3 pi by 5 by 2. Okay, this one, and send it. Okay, send it. So this is also a way, but we will directly write now. What we, as you said, is h of e power j omega magnitude cos of same frequency 5n plus angle of h of e power j omega. Right? So this is what happens. Okay, when you send the cosine signal or sinusoidal signal. Okay, no need to write x of e power j omega explicitly in this case. Okay, right. So now what is magnitude of h of e power j omega? What is h of e power j omega first of all? So we'll go to the next page. What is h of e power j omega? Explicitly, j omega by 10 t. Okay, so it is equal to j into omega into
10.
Okay, so this is 10 into j omega. Okay, so this is my h of j omega. So magnitude of h of j omega is equal to how much?
10 omega.
10 omega.
10 omega.
10 omega.
Angle is how much?
Pi by 2.
Yeah, tan inverse of, okay, like whatever, y by 0, so 10 omega by 0. Okay, so it is equal to pi by 2, right? Okay, so now what do? I will write here as, so the cosine signal when I give to the system j omega by 10. Okay, the this is h of e power j omega, and input is cos of 3 pi by 5 n. Output is 10 omega into cos of 3 pi by 5 into n. See, output, right? Mod. So where should this be like evaluated? See here I have written h of j omega, but where this should be
Omega equal to 3 pi by 5.
omega equal to 3 pi by 5, omega naught. Okay, so here omega naught, this also has to be operated at omega equal to omega naught, where omega naught is equal to, okay, 3 pi by 5. So you can see from here, this is omega naught. Okay, right? Okay, so it has to be operated at omega equal to 3 pi by 5. Okay, and plus pi by 2. Okay, now here it is independent of omega, so we didn't have that problem. Okay, so the answer now, what is this y of n is equal to what? So 10 into 3 pi by 5 into cos of 3 pi by 5 n plus pi by 2. Okay, and this is equal to how much? 6 pi cos of 3 pi by 5. So what is this cos of some theta plus pi by 2?
Minus sign.
Yeah. So minus I have put here sine 3 by 2. Okay, this is the answer. Okay, so what I have is y of n. So if I want to do yc of t, what do I do now? Yc of t, if I want to write, what should I do now? Replace
N with t by t.
okay, right here. So you can write minus 6 into sine. Okay, nt means, okay, 6 pi t. Am I correct? No, because 2
Yes.
pi by 10, you will get n by 10 is small t. Okay, 6 pi t. Fine. Is it correct or not? Yeah,
Yes,
right.
sir.
Now you got yc of. Very good. So what is the operation happening? So xc of t you have seen as 6 pi into what? Sorry. What is xc of t? Cos of 6 pi t. Okay, and yc of t is this. How do you think yc of t is related to xc of t?
Differentiators.
Yeah, very good. D by dt of xc of t. Okay. Huh? Can you like relate this to something of the system? So what is that system doing now?
Sir, high pass filter.
High pass filter.
Fine, it is working as high pass filter, fine. But more than high pass filter, what is the operation of the system? What is the operation of the system?
It is differentiating the inputs.
Right. It is differentiating it is acting as the differentiator. See here it is a discrete, a digital differentiator. Okay. So why do you think it is differentiating? Do you need to do all this? Without doing this, can't you tell is this a differentiator system or not? If I give you just this. Huh? Can you tell or not?
Yes, sir.
Yeah, how will you be able to?
Yes, sir. In h of e for j omega, we have this j omega.
Right. So
The Fourier transform differentiation is this j omega.
right, Fourier transform differentiation is j omega, or y of e power j omega, okay, is equal to x of e power j omega into h of e power j omega, right? Okay, so here omega into something x of e power j omega term will come. Where do you get omega into x of e power j omega?
In differentiation.
Yeah, in differentiation you will get. Okay, so this is roughly a discrete differentiator for, okay, x of e power j omega, right? Oh, that means discrete differentiator for x of n. Okay, or in continuous time it is exactly doing differentiation, right? It is different in time. Okay, please note that differentiation is not in frequency domain but in time domain. Time domain differentiation is amounting to frequency domain multiplication with omega, and hence See, multiplication, why did somebody has said high pass filter and so on? Why did you tell that this is a high pass filter?
Sure. The frequency becomes zero at zero frequencies. Around zero, there are zero.
It is zero frequency, it is zero. And then what's happening?
At high frequencies, it has magnitude values.
Right. So if you sketch it, what is happening? You see, the spectrum will be like this, something like this. Okay. So if this is minus pi and this is pi, okay, the spectrum is like this. So it is like a attenuating low frequencies and passing high frequencies, and hence this can be considered as a high pass filter. Correct. Okay. That's what is the differentiator. Differentiation means you are seeing wherever is the change happens, you are highlighting it. Okay, in time domain, if there is any change, variation happening across the signals, okay, that is highlighting, you are highlighting that. Okay, that means say minus 10 to plus 10, you give even 20 is the value of differentiation. Okay, 10 and 10, then there is a differentiation is zero, no variation, smooth. Okay, so you are identifying the variations here, highlighting the variations, that is exactly the operation of high pass filter. High frequencies, variations are high enhanced, the smooth, like no variations are suppressed. Okay, fine. So bit B, we will not do fully, but I will just ask you so your comments on this. B xc of t is given as cos of 14 pi t. Okay, so how is this problem different than the earlier problem?
So here aliasing will happen.
Right, here aliasing will happen because you see that capital T equal to 1 by 10 seconds, or f is equal to RFS, okay, is equal to 10 Hz. Whereas maximum frequency here, okay, in this FM is equal to 7 Hz.
7.
Okay, so it is okay less than 2 times the maximum frequency here. Okay, and hence aliasing happen. Right, and hence so there is some effect of aliasing. Okay, so that we will see now. Quickly we will see. So now you can write this as cos of 14 pi t, we replace by what?
N by 10.
Yeah, cos 7 pi by 5 n. So is this do we go with this, or should we do something? Do we rewrite this? This is exactly equal to what? This is exactly equal
Cos
to
of
2
2
pi
pi
by
plus 2 pi by 3. 2 pi
what is
Cos 3 pi by 5 and minus 2 pi.
right? So this can be written as cos of 2 pi minus, okay, 2 pi n minus, okay, 7 pi by 5 n. Okay, so it is roughly cos, this is equal to, sorry, yeah, 3. Okay, so this can be written like this, and this is equal to this. Okay, 2 pi n you can knock off, because I think 2 pi minus theta is same theta. Okay, so you can see that this is 3 pi by n, 3 pi n by 5. So where is, have you seen the signal x of n? Cos 3 pi n by 5. Have you seen the signal
before once.
Yeah,
Yes.
this one is cos 3 pi n. Okay, so same output you will get, and hence, okay, yn is exactly equal to whatever I got here. So what is that? Minus, okay, 6 pi into sine, okay, sine 3 pi n by 5, and then yc of t is also equal to minus 6 pi into sine 6 pi t. Okay, so now you see, is there any what do you see here now? When you given a signal cos of, okay, 14 pi t, okay, analog to digital converter, okay, and then you are giving to this filter, okay, and then you are this reconstruction yc of t. What's happening? This is not exactly differentiator, okay, so it doesn't differentiate. No, yc of t, xc of t is, you cannot write yc of t is equal to, okay, d by dt of xc of t. Okay, it's not time domain differentiator because of aliasing has happened. Okay, right? Is this fine or not?
Yes, sir.
Yes, sir.
Okay. So, like in continuous time, discrete time things doesn't work. Okay, see, if I would have given this xc of t to a continuous time filter, j omega, okay, is my continuous time filter. Okay, then I got yc of t. So j omega means what? It's also exact, say h of j omega is equal to j omega is my filter. Assume that. Okay, then what I'm doing now? Exactly yc of t is equal to d by dt of
X of
x. Okay, differentiator. So whatever I give as input gets differentiated and comes as output. Okay, but whereas, okay, in this case it is not the case, because there may be a possibility of aliasing which will change the signal itself, discrete signal itself. Okay, so a equivalent of differentiation will happen, but the frequencies will be different. Okay, can be different. Okay, fine. Okay, so if you have any
Okay.
questions you ask, yeah, we will wind close the class now. Yeah, thank you then.
Hello, sir.
Yeah, thanks and bye. So you prepare well. So for the small quiz that will be held shortly, and also for the class test also, I would suggest. Okay, and keep going on the other aspects. Okay.
Hello,
Fine.
sir.
Please tell Vaishnavi.
Yes, sir. So, what about the test today, sir? Can we
Yeah,
keep the class test today?
yeah, you can.
Yesterday, it didn't happen.